Welcome to Discrete Mathematics for Computer Science. I'm Professor Ayman Alzaid, and I'm glad you're here. In this lecture, we begin Unit 4 on set theory by exploring one of the most fundamental ideas in all of mathematics. What does it mean for something to be a member of a set? This seemingly simple question underpins database queries, programming data structures, logic, and formal proofs. The two symbols you see on this slide, the epsilon is an element of, and its negation is not an element of, are the primary tools we'll be using today. Let's dive in. By the end of this lecture, you should be able to achieve 6 learning objectives. First, define a set and describe what membership means. Second, correctly use the membership symbols in your notation. Third, distinguish between roster notation and set builder notation, two distinct ways to describe the same set. Fourth, apply membership tests in both mathematical and computer science contexts. Fifth, recognize the standard special sets: the empty set, the natural numbers, the integers, the rationals, and the real numbers. And sixth, write and interpret precise membership statements using proper mathematical language. A set is an unordered collection of distinct objects called elements or members. We typically name sets with capital letters A, B, S, and we list their elements inside curly braces. Here are 3 key properties to remember. First, order does not matter. The set containing 1, 2, and 3 is absolutely identical to the set containing 3, 1, and 2. Second, duplicates collapse. If you write the same element twice, the set still contains it only once. Third, elements can be anything: numbers, letters, people, even other sets. Look at set A on screen. It contains 4 elements: 1, 2, 3, and 5. Each one is a distinct member of A. To express membership, we use the Greek letter epsilon. When we write X is an element of A, we read it as X is an element of A, or X belongs to A. Its negation reads as is not an element of. These two symbols encode a binary relationship. Something either belongs to a set or it does not. There is no middle ground. Let's look at a concrete example. If A equals the set containing 2, 4, 6, and 8, then the statement 4 is an element of A is TRU or does appear in the set. The statement 7 is not an element of A is also true. 7 is not in the set. But 2 is not an element of A would be false because 2 is indeed in the set. Practice reading these statements out loud. Precision in notation is a core mathematical skill. There are 2 main ways to write a set. The first is roster notation, also called enumeration notation. We simply list all the elements explicitly separated by commas inside curly braces. Example 1. V equals the set of English vowels A, E, I, O, U. Example 2. P equals the first 5 primes 2, 3, 5, 7, 11. Example 3. E equals the even non-negative integers written as 0, 2, 4, 6 with an ellipsis. The 3 dots show that the pattern continues infinitely. Example 4. D equals the divisors of 12. Roster notation works beautifully when the set is finite and manageable. For large or infinite sets, we need a more powerful approach, which brings us to our next slide. The second way to describe a set is set builder notation, which is far more powerful and compact. Instead of listing every element, we describe the property that all elements share. The general form is the set of all x such that some property P of x is true. The vertical bar is red, such that. Look at the examples on screen. All even integers. The set of x in the integers such that x equals 2k for some integer k. all positive reals. The set of x in the reals such that x is greater than 0, divisors of 12. The set of positive integers x such that 12 mod x equals 0. And in computer science, you will often see set builder notation to define formal languages, for example, a set of all strings over alphabet sigma whose length is at most 3. Mathematics and computer science share a common vocabulary of special named sets. The empty set, written as the empty set symbol or as empty curly braces, contains no elements at all. It is the set theoretic equivalent of 0, and it appears as a base case in many recursive definitions. The natural numbers are 0, 1, 2, 3, and so on, directly corresponding to array indices and loop counters in programming. The integers include all positive and negative whole numbers, matching signed integer data types. The rationals are all fractions p over q, where q is non-zero. And the reals include all rationals plus irrationals like pi and the square root of 2, corresponding to floating point numbers. Notice the containment. The natural numbers are a subset of the integers, which are a subset of the rationals, which are a subset of the reals. Each set is a subset of the next. Let's solidify this with worked examples. We have two sets. A equals the odd digits 1, 3, 5, 7, 9, and B equals the first 5 letters A, B, C, D. Go through each statement carefully. Is 5 an element of A? Yes, true, because 5 is in the list. Is 2 an element of A? No, false, because 2 is even and not in our set. Is 4 not an element of A? True, 4 is not an odd digit. Is C an element of B? True, C is one of the first 5 letters. Is Z not an element of B? True, Z is not in our set. And finally, is A not an element of B? False, because A is in the set containing A, B, C, D. When you evaluate membership statements, always refer back to the definition of the set. Do not assume, verify. Let's summarize the 5 key takeaways from this lecture. 1. A set is an unordered collection of distinct objects. Order does not matter and duplicates are ignored. 2. The membership symbol expresses membership, and the non-membership symbol expresses non-membership. 3. Roster notation lists elements explicitly. Set builder notation defines them by a shared property, know both, and use them appropriately. 4. The major number sets, the empty set, the natural numbers, the integers, the rationals, the reals will appear throughout this entire course. Memorize them. And 5. Membership is strictly binary. For any x and any set A, either x is an element of A or x is not an element of A. Every element either belongs or it does not. No exceptions, no ambiguity. Congratulations on completing Lecture 1, Membership of a Set. This is the cornerstone upon which all of set theory is built. In our next lecture, we will explore subsets, when every element of one set also belongs to another, and set equality. Before then, I encourage you to practice. Take any collection you encounter in daily life and write it as a set using both roster and set builder notation. Try asking membership questions and verifying them precisely. The habits of precision and verification you build now will serve you throughout discrete mathematics and beyond. See you in the next lecture.